Hello and welcome to another video. So just picking up from where I had been. In statements, I've recently added a MOV, and so I kind of pardon me, got my throat. I kind of ended on a partial work in progress. It wasn't doing everything, and in the meantime, I had also kind of added all these static assertions, so it kind of complains a lot. Kind of forces you to implement before hitting the runtime assertion. So at the moment, it does that. I have actually done a tiny bit more, a bit of copy pasting from other stuff. Way to make him move, way to actually detect it, and return the correct token. And then in parsmov, I've basically copied that from parsdb and then changed a little so it makes sure that you have a space between the mov and the next thing. I think that's like kind of unreachable because if there was something straight after the MOV, it would get treated as what do you call it? A just identifier as MOV 123, whatever it is. But yeah, so then it passes the destination, and then it basically skips all the white space and comments, and then which I think the parse expression does for me, but what I want to do is actually check that I have a comma coming up in between them. And so after I get that comma, I then look for the source expression, and at the moment, they will just get treated as like registers aren't treated any differently. It's just how it is. And so then kind of I have a bunch of debugging stuff. I kind of make a span that kind of fills the entire thing. So all the way from the end of the source to the start of where you see MOV. And that's pretty much what I've got on my diff. And at the moment it complains because if we say for example bump that up, um, it actually breaks further up on the same switch. Like if I search back for switch, this is the one that I've changed. So what I might do is add in mob type thing. So what do I want to do? I kind of want to make sure that the I have a mob object, something like that, and once I have that mob, I then want to compute the expression of the source, I guess. So that would be the mob source expression with the current scope, and that should get back a thing. And we can make a little thing if we can't get it, and perhaps make that a source expression. And then we kind of need to make sure that it's not that. And I wonder if we want that debug stuff as well. it might be handy in case something isn't working. So if we can do that, so computer expression, do that. This is times that mod. So if it is a string, that doesn't really make sense. So we have a thing for that. So we can kind of do that. And so this will be, we can just do computer expression dots. So at this point here, we should be able to get a number that's enough to kind of go off. So we should be able to get a number out of the expression, and we don't care about positive or negative at this point. It now kind of depends on what our source is based on what our range detection is going to be. So, how do I want to do this? So, thing is, we yeah, perhaps make that. Actually, no, maybe I'll just get rid of that for now. So, what I want to do is make a computer expression of perhaps a no, an expression. How do I want to do this? I kind of want to just have a list of registers, and it probably comes in a particular order. So like for example, this is B0 plus B, which is the register number, and so I forget where this kind of talks about registers. So register. These are just all the instructions, aren't they? x86 registers. Like I know, like all the orders, but golly, not bot. I swear. Like there's all these, but like what order is it? Like, is this the order? How do I know what order this R8 is? Um, just this kind of x86 assembly register value like yeah. Because I need to know the order so I can make it enumeration in the right order. EAX. This one seemed interesting. It just get to see me searching. This So register, golly, and it not showing me enough text. Oh no, that's kind of a little opaque mystery. What we can do is, so we can kind of have this, and so we have like a AH, we have an AL, perhaps we do that. So what do I know of EAX, EBX, ECX? So I have a feeling that and like what if I do that sort of thing, and we can maybe do that and then that and then that didn't work, but yeah, that did. And then that can be like that. And just maybe one more just to see that it's doing the thing that I wanted, and then that wanted to be like that. Just the one. And then what I can do is Phasm of that and have a look at the output. And we can see, so this, the, what is it, the mob of the kind of format that I'm doing of, well, I'm also doing 16s in there, so we might see some different bytes kind of being assembled. So we see B401, and so that means the first thing I did, which was the AH, is kind of set to 4, then AL. And perhaps I should kind of note these down. Define days and registers. And this is really like x86 registers. So which one has the, oh, so it's B8 plus that and B0 plus that. So which one is B0? That was AL. So XAL. And then this one was a long one. So that was the 16-bit one. So B8. And B8 plus 16. So that means that this kind of has 16-bit registers. So we're going to have kind of two different things. And this was AX is allowed for that. And so this was actually 8-bit registers. So what was the next thing that kind of comes up? So I'm kind of looking for B1, which kind of happens right there with the 8 with CL. Like this order is kind of weird. Like what did 5 get put as? That got put as B3. I'll put it in because this is the order that I'm going to use to be, that needs to be that plus that. So, CL was the one that went to that, so we go to CL, and then B2, does B2 even show up? No. So perhaps I need to kind of do this. And how many were there? There was so we just go up to DL and then we get like these special ones. So we really just, I kind of want to get rid of the X's and then we can do the D, and I guess that means we can go down one couple, and that kind of magically lined up. And now we want DIO, SPO, DIO, that one, and then SPO, and what was it? BPO. So if we present that, we're not allowed to do that. Okay. There was also SIL, but doesn't want that to happen. And we're not allowed SIL as well. That's right, we're not allowed SPIL. And I would imagine that we're not allowed the last one as well. Cool. So if we have all of these kind of done like that, we should have a bunch of things. So and then if we kind of that, we should be able to see 0 is 2, so AL. Then we should have a 1 is 6, which is CL. And then we have 2, which is 8, DL. Very odd order, DL. There's probably like an electrical reason why it's not A, B, C, D. But yeah, so we had 2, we had 3 end up. B3 is for 4, and so that's only get the BL. So B4 has 1, so that's AH. B5 is 5, CH. So again, it's kind of skips that. B6 is 7, DH. And there was no B7, was there? Because that should be there. So to kind of resort these, so we would have something more like that, and then we would have BL at the end. And now if we kind of change up these numbers, we can confirm that all the numbers kind of add up. So it's useful to have an assembler that does it for you, but here we have B 0, 1, 2, 3, 4, 5, 6, 7. And so I can say those are the orderings that they want. And I guess while I'm here, I may as well kind of do the hypothesis that it's that order for the others. So maybe I can do that and that and then that and then that and then that, and then we can see what that kind of goes to. And then here we can see it's B8, B9, BA, and then BB, showing that kind of order for these ones. And we can potentially chuck in the SIDO, SPBP, but it might not make sense. So what was it? SIDI, SI. I didn't actually want that like that. BP and SP, FP and BP. And do you, as in that you do. All right, let's change these numbers up a little. Do something like that. Cool. So if we do that, we have B89AB. We have C is 7. and D is 8. So those last two need to come back to. So these two can come back to there, and then that could be 5, 6, and then 7, 8. And so now if I do this, it should be roughly in order 8, 9, A, B, C, D, E, and F. And so that is the order of the other ones. So we have C, then D, and then back to B, and then SP, then BP, and then SI, and then DI. And these ones are like kind of shortish, so I kind of wonder whether I find that and then go there and then go like that and then did that not do that? No, we need to do a norm first, and then from there we can just have kind of one, and I think that's potentially okay. So then we can have these two that we can kind of start getting the right things. So we can ASM x86 8-bit registers and ASM 8-bit bit registers, and this can be register T. I'll just call it T. We don't need to have the names. We can have the strings for them, I guess. We also have x86 8-bit register, x86 8-bit register. I think I will get rid of these kind of things. On that, yeah, you can. Cool. And here we should probably say this is x86 as well. And so this we can find the 8 and then 8 more in them, and do that in a few places. Cool. And then here we can have the strings of them. So here we can have x86 8-bit register strings and something like that. And then find the 8 and then 8 more of those. Here we want ASM x86 except ASM x86 8-bit registers, do the same there, but then find the 8, and 8 more of them. And so now we need to find those registers that we kind of did, and then I'll get rid of that and that. So now we have those two registers, if that kind of makes sense. I wonder whether I want to. Yes, I can do this. I kind of want to call this a string view T of the register strings, and it I think requires a different macro here, undef x. So here we want to do a string view of whatever the C string is of that, and it will do that. And so we also want to do that string view T, and then we kind of just have string views instead of C strings, which can be a bit nicer. So what does it not like here? But is it not? I didn't want to do that. Is it not? Do we need a... Can we do something like this? Do I need to like manually make it so we can have a string view t, and the data is going to be that, and the size is going to be len of. Can we do that? And we probably need to have that. So no, so it doesn't like this. Not a constant expression, but I thought it would be like a macro time thing. I guess that's unfortunate. I will just go back to this, and so we can kind of just const star that and does the same thing. Cool. So that is that. What doesn't it like? We're not using them, so we should have the statement for execute. We want to execute the statement. So here we should have a computed expression that works out to be a number. It will kind of complain if you do a different thing. This might need changing when I add support for different MOV things, but perhaps I won't. Who knows? So after it gets this computed expression, we get a number out. We now need to work out what type of destination we are going into, and I feel like we should perhaps do that before like computing the thing, just in case that computation can be a bit more. So what we can do is we can dest string dest view, and this can be we do have it, so it will be statement, and we have a destination dot span. So this thing here, we can now do like a string view. So we have a CMP compare. We have a string view compare, and what does it take? It takes another string view. That's kind of why I want it as another string view. So what we can do is we can compare the dest view, and we can compare it with a string view of each register that we have. So what we need to do is for size t I equals 0, I is less than anything num. So I guess we see if it's an 8-bit one, and then we can see if it's a 16-bit one. It's kind of yeah. Just trying to think forward planning, like where will it end up? But at this point here, we can get that, and we know that this is less than the number of things that is there, so we can just make a string view out of the string that is in there, which is unfortunate because it means we need to basically look up the length of the string every time, which is could be pre-computed. Right, so if this is equal to 0, I guess what we want to do is we also need a none, I guess. I kind of like the order that it is in, so what I want to do is we can have a 8-bit register T, um, rig 8, and we can call this ASM x86. Well, we can call it num x86, that one. And we can also find the 8, can add 8 more, and we can do that a few more times. So that way we can kind of see which register it is. So, we could even desc_view.size equals 2. We do this, otherwise we do another thing. Are we allowed to go back there? Otherwise, maybe do an unreachable, unhandled destination, and perhaps we can string view fmt, and maybe we can quote it how we've been quoting everything, string view args, and we can pass in the statement.destination.span, that one there. And so that means we just need to implement it. So if one of these strings match, we can then set reg h equal to I, and then we can break. And so then here, if reg 8 not equal to ASM num, if it's still equal to that, I guess, then we can kind of do the same bit for 16 bits. So here we can find that 8 and then 8 more of that. Same there, and then that same there. And that one we want to keep there. And so at this point here, we it can actually do something like this. If actually no, there'll be, because like the 32 and 64s are all 3-bit, and these are all 2-bit, 2-character length. Trying to work out which one you want to iterate over to do the string comparison on. But what I can do here is if we have reg 8 equal ASM num, see, I kind of want it to be none, ASM, and that kind of means register. So we'll have x x86, and these should potentially all have like ASM x86. 86 register, probably something like that, and perhaps I can do something like that, and because of that we probably do actually want to do something like that. and do that a few times, and then we can register none. And when we come to check it, so if we kind of go here, we can have this to be ASM x86 register none. And maybe we can call it number 8, because this will need another thing just because of what it is. And perhaps here we can make that 8. I probably should have. I mean, the 8 can potentially go here. I'm like bike sharing, but it is what it is. So here, if we like yank all of that, that's not actually what I wanted to do, but what I could do is yank that and basically do the same again, do that on everywhere, and then perhaps just do that same macro that kind of just works. And then here we just need to, can we do this in a, no, we can't, but we can do that and that and that and that and that and that and that. And then we probably also want a none at the front, and we'll just have to remember that we have to subtract 1 off the actual enumeration value before doing a thing. Duh, duh, duh. So, when we get back to this, we never use that. That is quite frustrating. So one of these. So here we will have 8-bit register none. Do that. You can maybe just get that, and then we can get that up. And that has the benefit of this. We can, if not rig 8, and that kind of simplifies that a bit more. And here we can just, if not rig 8 and not rig 16, we can kind of track in that little message there. And I think for now we can just do that. And when we have support for the 32 and 64-bit, we can kind of just add in an extra check there. So once we get our register, we can now compute the registration. We get the number, and I think at this point we have enough information to write some bytes. So if we kind of look at the, I'm more interested in the 8-bit for now. If we look at how we did that, and so in here we have we need to output. Can we get rid of this? This has a that thing, and I want to write some bytes. So the bytes that I am going to write, and this is what I was wondering about before. We do have this. So if I print C a character and that character is null, does it actually print the thing? So we can't see there, but if we kind of do this, we can see that it does indeed print that. Cool. So we can do that. So what I want to do is we're going to print 2 bytes, and we can XXD the right thing. We can see what the 2 bytes are going to be. So the first off, if reg 8, that means we have found a 8-bit register. If number is greater than 255. So where else do we do that? We can kind of support both of these. What happens if we just trying things? What happens if we output a -1 as a character? Do we just get FF? We do just get FF. Cool. That works as I would expect it to. Cool. So we want to get this and do that same bounds check there. And we can kind of output the thing. Otherwise, we can reg 16. I guess we can do the check because we could theoretically do that 16-bit because I kind of put it in. So golly, maybe I'll get Python and so 16. We can kind of go up to that number, 65525. But what is the like negative equivalent of that? It will just be like divide 2, and so this one gets the half, so it'll be 32768, and then this one does not get the half. And then here we can say 65535, and this is 32768, and 27, 2767, that can be 8 there, and 65535. Cool, and then at that point we should have enough to go on. But I think I almost want to kind of bring that in here because the output is different depending on which one it is, and so perhaps here I'll just do a to-do output something, but and we can come back to that. So at this point here, we're appending the byte, and the byte that we wanted to do was 0xb0, or we can do plus. So it's plus the register value that we have. So what we want is the reg 8 minus 1, because we know it is something. And then the next thing that we want to do is the immediate, and that will just be that number. So yeah, maybe I'll do the 16-bit. So the 16-bit is just B8, and then it does both the words, and we can probably what about put these ones again? So if we FASM XXD that, here you can see that it is in a little Indian order. So basically, you read the numbers backwards. So it's 0001, 0002, but the first byte is always going to be there. So what? How do I do that? Because we've got this Yeah, I'm kind of outputting each byte as it is. I don't want that though. I just want this down here. So I want each byte as is. It first starts with that, and we can kind of get a 16-bit one. And so the first byte that we want to write is going to be the number, the low end of the number. So we will kind of 0xFF that. And the next byte we want to shift down by 8 and kind of get that number and perhaps do that. Perhaps this should be, I don't know. We don't do it in other places, but perhaps we should, like here, we should do cent 0xFF. And that's kind of all the places. So I think I just need to take out that to do, and we can probably try this one. Yeah, that one. Cool. We've got a few years. So what I can do is make sure we're testing the same file and see what it is. All right. So we don't have destination, but we do on the MOV. Cool. We are not allowed that because that is a const. How can I say that this is also a const? No, it's because we're putting it in the data. So I think this, these two, we kind of just need to not be const. So this statement was the MOV, and that's that. Cool. And now we get unhandled destination. So that is interesting. I like how I said just after so the problem is that we have uppercase things for this, and because I changed all the names, all the strings are not right. I just realized. What we can do here is we can pass in a string, and it can just be perhaps a null there, and we can do some queuing. If we yank that, then we can go S, paste that, and then start at the same place. And then I think we can just go like that. One more. What if I add in that and then do that? Yeah, that kind of works. And so here we can null, and I think here we can just kind of add in the h times we need to do that, and we can kind of keep that on. So that means that these kind of need their own kind of thing. So we will have to define S to be just nothing, and I guess we can do that definition there. But then here where we use this, so we want to undef X. Yeah, this is what we want to do, and then this is what we want to define X of code to be nothing, and then S of code, and this can be our strings. So it can just be that, and I wonder if we can do a string view of that. And I wonder whether that will kind of let me do that. No, we don't do that. That's all good. S is redefined, so we need a X at the start of that. We can perhaps kind of do that. undef s. Right, and cool. So we not allowed that. So we will just have the strings like so, and then here we have that, and I guess all of these need. Well, I wonder if I can. No, I can't do that. But what I can do is do something like that, and then do that 6 more times, and then that was like 8 more times, and do something like that. Cool. Now it should get the right things. So I did notice it errored out on a seg fault. So we're getting strlen of a thing that we can't get. So 2116. That's what we are doing. We want to actually start from 1, not from. I mean, what we could do is reg 8 plus 1. Rig 16 plus 1. And I wonder if we can call these ASM x86. These ones are these there. So we can do that. We can do the same thing here and then find the one that minus it. And then it kind of is a bit type safer, I guess, so we'll kind of know what to do. So now it does that. And it still doesn't know so now I'm back to the original problem that I thought it was. If we doing this comparison is case sensitive. So what perhaps I might want to do is like there's strcmp, which will do this, but there's also strcasecmp, and I think that's kind of what I want to do, ignoring the case of the characters. So what I think I want to do is case compare. It's kind of a weird name, I'll be honest, because like when I see case compare, I kind of think, oh, cool, you're comparing the case, not ignoring the case. If like, but it is what it is. I'll kind of adapt to what it was, and so where we had compare, we'll also have a case in CMP as well, and where we have this, we can just kind of copy that, go down to this new one and go case CMP, and then here we can do something like to lower of that character and to lower of that character. And if they are different, what do I want to do? I kind of want to make sure that I am getting that right, because you want the difference of what it is, and if one's like quite odd. Cool. So I think this is like all that I need to do to be like, cool, we now know how to do things, and we read some bytes, but we couldn't parse it. Expecting equals at this point here, and that's because we've got this int. I'm going to just comment out that int just for the sake of this, and we have now written some bytes. And if we see what bytes we have written, I've written that to test. So what I kind of want to do is x86 BIOS. Mine. The T is like a function in well, in fact I can go like typo T, is that what it is? Which T and T Yeah, type T, not type O. And then we'll show you kind of all it does. But yeah, so you see here I've done this, and it is put in a B4 OE BO F4. And I don't know if that's right or not. But what we can do is if we phasm the same file, I guess, test.bin, if we get that, we get the same output, B4OE and BOF4. And so we've successfully assembled two instructions, I guess. Well, one instruction is a move, and it's only a very limited, so I'm only doing two types of move. But I can move through more and more and do more. And I can also choose which ones not to implement in my source code, because I might decide I want to focus more on the operating system at some point, and I might decide I don't really want to care about the assembler and what it supports and what it doesn't, and I can just use what it supports at the time to get what I need doing. So I think what I'm going to do is add up this into a little commit, and we can call this done. Finish off Mov. And so this was on another branch. I can't push as well, but we can switch back and we can like merge in the thing that we just did. And it's a fast forward because I didn't do anything in the meantime, but that way we can kind of get a history. And I did it off on a different branch so that I knew main, the tip of main is always buildable. And so I guess another thing I should do is run the entire test suite to make sure that it is still doing the thing that I want it to do. And it looks hopeful. Yeah, cool. That looks all good. So that's another instruction done. Thanks heaps for watching. I'll probably leave it here and be back in another video to put in some more things. So, I mean, if we do that one more instruction, and which we have enough to do, that will get us displaying something on the screen, which would be quite exciting. But until then, thank you for watching, and I'll see you next time. Yeah.